Good morning, everybody, and welcome to the second part of the second week. We are still getting this thing going. Since last week, we only had one session because of the holiday. So this week, actually, we also had a lab. Some of you basically have seen this content a little bit moving from the introduction right to the waves. This is, again, I explained it during the lab session. It has to do with how the labs are flowing in the college right now, so we're trying to adjust to that. So the first week we basically introduced, and we continued with it this week, waves and wave phenomena, oscillations in general, and then those are localized as opposed to waves which are traveling. Then we went to the lab and we basically we introduced also the concept of resonance for waves, or standing waves to be more specific. And we were able to go into the lab and basically do the resonance in a sense, trying to find where we can find the tone or the sound to be the loudest. So that's what the purpose of the lab. And based on that, we determined the different basically modes of oscillations or vibrations of the sound. And we're using the dispersion law, namely that relates the velocity, the wavelength, and the frequency. We were able to relate these two, and the purpose of which was to plot that dependency and have more or less a linear dependency, proving the dispersion law in this case. Okay, the dispersion law, as a matter of fact, if we follow not the instructions in the lab, but the instructions I gave you guys during the lab session, where instead of plotting f as a function of lambda or lambda as a function of f, it doesn't matter because both of them are symmetrical, interchangeable in this situation, because they're a product of one another equal to a constant. They will give you some sort of a function that is not easy to interpret. However, if you plot f as a function of the inverse of lambda, for example, or you do the same thing. As a matter of fact, you could take lambda, the wavelength, as a function of the inverse of the frequency. Then in that situation, in either case, you're going to end up with a line. The slope of that line is the velocity. If you put it in the correct order, f will be basically 1 over lambda times the velocity. So the slope of the graph then would really be the velocity of sound that you ended up with. Granted, for each measurement, we were at some point checking the velocity, but that's not really the idea. Is to see that linear dependency between the velocity and between the frequency and the inverse of the wavelength. The slope is the velocity. So that is the key thing that we took from that lab. And you should have a space for it where to submit your lab report, and the concepts we covered in lecture, they were there also in the lab. Today, we're going to build on those concepts. We have, when we discussed the interaction of waves, and we took the example of an incoming wave from one end and an incoming wave from the other end, and when they collide, they may interfere constructively if all the right conditions are so, in a sense that they come in phase and they go up. If they come completely out of phase, one of them is pointing up, the other one is pointing down, then they will cancel completely, provided that they have the right amplitude also, meaning that they have the same height. They have the same height and one of them is positive and the other one is negative, of course they will cancel. And then after the collision, they will emerge intact from that collision. And that has a fundamental reason for it, and it has to do with something called the linear condition. Because the wave equation is linear, meaning two waves can superimpose to one another. They can add up, basically. And the addition, the sum of the two, is actually also a wave. So that's basically the idea behind it. That's really in other words, satisfies the same conditions of a wave. So that's why when they are far apart, they're still two waves, and their addition is actually a wave. So when they superimpose, that's still a wave, and it's just the addition of the two. One of them happened to be negative, though. And then when they emerge the way that they came in from. Now, those are all basically how waves interact with one another. As a matter of fact, that concept of adding waves was really needed to introduce the concept of resonance and the concept of standing waves, because in the case of a string, for example, that is fixed from one end and you're continuously pumping waves from the other end, pushing waves from the other end, you have one that is moving to the right. The minute it hits the wall, it's reflected. And because it cannot go up, because it's fixed in that end, so it's going to be reflected and out of phase, meaning that it's going to go in the opposite direction. So if the first one is coming up, the second one it reflects down. If the first one is coming down, the one that is reflected is going to go up, okay? Because to satisfy the condition that is fixed in that point, in the end. So at the end, what you have throughout the entire string, you have waves that are coming from one side, from the source, and waves that are reflected from the fixed end. Now, they don't necessarily form those good shapes because the condition of resonance is that they have to have a matching frequencies. In other words, they have to have the right amplitude, they have to have the right frequency, so that happens. And when that happens, that is a resonance. It's the condition. That is the resonance. That is the standing waves. So the string, if you try to experiment with it today at home, you fix a string from one end and you keep on doing it, most of the times, you're not going to get those shapes. You really have to hit it with the right note. That depends also on the length of the string. That depends on how much the string weighs. Once you know those things, you can actually calculate the fundamental frequency. Once you calculate the fundamental frequency, then you hit it with the right tone, which could be the fundamental frequency, or twice the fundamental frequency, or 3 times the fundamental frequency, or any integer number of times the fundamental frequency. In either of those cases, you're going to produce either a one basically NT node and 2 nodes, or 2 NT nodes and 3 nodes, or 4 NT nodes and 5 nodes, and so on and so forth, depending on the frequency that you put it in. And that's what actually a person playing with a musical instrument like the guitar does. So if you hit the string not in the right fashion, you're not going to produce a musical tone that is going to be at least pleasant to the ear. People will not appreciate that. So you really have to be highly trained to hit the right note on the right string with the right frequency and change accordingly, because there are several strings. Each and every one of them has a different tension in it. And each and every one of them satisfies the conditions for the propagation so that it has a different tone. And those tones are specific to that guitar. And the person who's trained on it produces those tones. As a matter of fact, he or she produces them in a sequence that produces a actually complete symphony, if you wish, complete output that is going to have a message in it, that's going to deliver something that is pleasant to the ear and a person enjoys it. Otherwise, if I go and play, you're probably going to run away because I am not good at it. I don't play at all. So it's going to come up completely messed up. So the resonance is really a condition that needs to be met in order to produce those harmonics. Okay, there is the fundamental frequency and there is the higher harmonics. And those higher harmonics are delivered again with the right frequency. Okay, so that is basically the point on a string. And that's true also for any kind of waves, even those for the case of sound and a tube, for example, the one that we did in the lab. Okay, except in that situation, it's not similar to a string that is fixed from both ends, basically. One end is producing source and another end that is fixed on the other end. In that situation, it's similar more to a string that is free from the other end. In other words, when you snap it, the other end is going to go up and down. Okay, it's not going to be fixed in points. So that's the only difference. So it's open from one end, and it's from the other end where you're producing the source of the waves. So this is the resonance in general. So let me share with you the screen so that you build up on the concepts we were talking about last time. If I can find my OneNotes, okay. And so instead of continuing with the I don't know what this is. What is this title? International. Oh, the system for some reason. Okay, never mind. Okay, so we're building on those concepts and sort of these things. It picks up my handwriting and sometimes it translates it weird. Okay. Are you guys looking at my OneNote? Please confirm. Which chapter 15, 16?
What was the question?
Are you guys looking at the OneNote, the screen I'm sharing?
Yes.
Okay, very good. Thank you. So basically, just to make sure that I'm sharing the screen, because sometimes I keep on talking and I'm in one area and the screen is lagging behind me. So let me make sure the color of the pen is correct. So basically, so here is the situation for the string, okay? This is not what we did in the lab. We did actually with the sound. So in the case of perfectly standing waves, again, I could produce the fundamentals. So this is one oscillation with one NT node. And of course, two nodes. In this situation, the two nodes, one of them is at the end and the other one is on the other end, okay? I could also do another situation where this is the source and this is again where the string is fixed in such a way. The first line in here that I'm drawing is actually where the string would be stationary if I don't produce on it any waves. So this is the same thing. So this is the string that is stationary. And then I will produce two NT nodes and one and three nodes, okay? So this is also a case of resonance. So between this one and this one, there is a gap where I could produce any nonsense. Basically, the string would look kind of a jobbly thing in there that doesn't satisfy the condition of resonance, and so on and so forth, okay? So technically, I could produce three actually NT nodes and 5 nodes. So these are higher harmonics. So these are higher harmonics. So again, the relationship between all of the frequencies. So if I give you frequency F that I measured first, okay? So I'm gonna put the label in here, okay? I'm not put it underneath for a reason. And I did another measurement F2. They are not necessarily spaced, okay? So this one could be 600 Hertz. This one could be 900 Hertz. And this one could be, for example, 1050 Hertz. Okay. So those are my measurements, for example, in this situation. And I ask, what is the fundamental frequency? The fundamental frequency, which is different from the higher harmonics, basically, fundamental frequency or mode. Then in this case, there is an algebra formula for it, and the algebra is the greatest common denominator. Obviously, these numbers, you can divide them by 10. Because if you divide 600 by 10, you will find 60. If you divide 900 by 10, you'd find 90. If you divide 1050 by 10, it's 10. So we'll be tempted to say it's 10, but it's actually more than that. Why? Because actually 3 also is a common multiple of this one. 600 divided by 3 is 200. 900 divided by 3 is 300. 1050 divided by 3 is what? 450? Or no, is it 450? No, is it 350? 350. Okay. 350 times 3, you have 3 times 0, 0. 3 times 5 is 15. 3 times 3 is 9, plus the 1 that I need to carry from there. Yeah, so it's 350. So all of them have a common multiple, also a common number that they can be divided by is 3. So the common value is actually 3 times 50, which is 30. But is it only 30? It's actually more than that. So if you are good with the algebra and how to find the least common multiples, the answer to this question is 150 Hertz. This is the greatest common denominator of all of these numbers. And I chose them as an example like this one. So this is actually what is known as the fundamental frequency. This is the least frequency I could form with the string. And I could form theoretically 300, which is twice this number, or I could find also 450, which is 3 times this number, or I could find also 600, which is already found, which is already listed in here. It's in here, it's part of the, that's why I was avoiding to label these things, what is the, to label these things with the indices, okay? Now this one has a proper index, and usually they give it the index of 0 to say that this is the fundamental frequency. In this example, it's 150, it's not always 150. For this example, it's 150. But then I found one of the harmonics of this fundamental frequency, and it's not the first harmonic. The first one is 300, the second one is 450, actually it's the third one, okay? And then if I want, there is another one, actually, after I add, there is a 750, and there is also 900, and 900 was listed in there, and again, here it is. So it's another harmonic. So that is basically the idea, what you hear, especially if you're talking about musical instruments and things like that. This word is repeated a lot, and that is basically what you need, you know, with it. So what is listed in there usually is the fundamental frequency, and you can form higher harmonics out of it. You have to be careful though, because strings, you have to really tension them correctly to, first of all, be on the right frequency. So usually for a musical instrument, you have a tensioner to adjust the tension in it, and the string may snap on you, so you have to really replace it there too. Okay, I don't know much about the music. I know the science behind it, but not really how to play it or what's going on in it and things like that. So this is one of the things that we have to understand in there. And there are some nice problems that you're going to be assigned to do. And of course, we're not going to be doing all of them in class, but we're going to discuss some of them in class. But then we're going to leave the bulk of them for our discussion before the exam, because you will have 2 parts for the exam. One which is a multiple choice part, and one that is actually doing some of these problems. Usually it's not are not hard problems, but again, if you find difficulty with any of these things, please let me know so that we can go on one-on-one. I mean, typical problems in here is that you do simple algebra trying to find these things, okay? So this is one of the concepts. Another concept that we were supposed to finish before we move to the next part, which is light, is the concept of beats. So what is beats? Now here is the situation. And this is actually used also in music a lot. So you have a source of a wave, which is wave 1. You have another source of a wave, which is wave 2. You have 2 waves basically coming from 2 different sources. And you have a receiver in here, only one. You sitting in there, for example, listening to a musical instrument. Think of these sources as amplifiers, okay? Coming to you. If the amplifiers are amplifying the same signal, there should not be any problem whatsoever, provided the spacing between them is not too big. So if this is the first speaker and the second speaker, and they're only within a few meters apart from one another, and you're sitting, especially if you are in a symmetrical situation, sitting right smack in the middle, you should not have any difficulty, because the 2 waves, they will come to your ears in harmony. They will come in the same time, at the same place, in the same phase, and they will add up. The signal will be amplified, and you will hear it louder, okay? But if they do come a little out of phase, then there is a problem. Then you're going to describe, find the difference in them. Okay, your ear is going to find a difference. Usually this is a behavior in time, temporal behavior. Let me tell you what I mean by that and why is that so. 2 things, meaning and then why. Okay, 2 things, okay? So what I mean by that is, remember waves, they behave in time. They have that oscillation, And they have also an oscillation in space. If I take a camera and snap a shot of the entire wave, it's going to give me pattern that is distributed in space. I'm thinking more in terms of the waves on the surface of the water, because that's easy to take pictures of. Obviously, you cannot take a picture of a sound wave unless I put it on some sort of a surface with some sort of a sand, for example, and that wave starts to produce that is coming in the air, produce some sort of a disturbance in there that I can see, or even somehow if I can take pictures of the, put some sort of a gas or something with specific colors, I may even distinguish that in the mass of air. So I may be able to do that. But the point in here, it's easier to be seen probably on the surface of the water if I take a picture of it, or even on a string if I take a picture of it. That is the spatial behavior. What I'm talking about in here is a temporal behavior. It's only space related to time. That is when we talk about beats, we are focused only on the time only. That is one thing. The reason why is that, so we answered the first question, and now we need to answer the second question, is because the receiver usually is in one spot, is not moving. Okay, so the person, even if he or she is moving, the two waves are going to reach that point in the same place. So the waves are reach the same point. So regardless of the problem, the waves are coming to you, your ear is in the same place, so you're going to receive them. So in this situation, the space does not really matter. Okay, if you have two receivers on one end and another receiver on the other end, then you have a situation here to talk about. Then you're comparing two different spatial places, so one of them receives it differently than the other. But in this situation, what we're talking about in here, and that could create interference too, and that could have problems too, but usually when we talk about beats, we talk about the temporal behavior only for two reasons. Because first of all, waves exhibit behavior in time, and second, because the receiver is in one's place. And even if he or she is moving, it's receiving the two waves in the same place. Now, the beats will happen only if there is a slight difference in frequency, or there is a difference in frequency. Beats, and I will describe what the beats are, occur when the two sources produce waves with different frequencies. Here is the thing. So if I have a frequency 1 from one source and I have a frequency 2 from a second source, the difference between these two. So if F2 is bigger than F1, I do F2 minus F1. If F1 is bigger than F2, then I do F1 minus F2. It doesn't matter because the frequency is a positive number, okay? So usually this is written in algebra as the absolute value of the difference between them. So if the difference is positive, the absolute value is positive. It means exactly this thing. If the difference is negative, then you take the other way around. You subtract always the smaller from the bigger. That's what this absolute value means in algebra. Okay, so again, just to not complicate it, we can basically express in the exact way of how absolute value works. That is that if the first value is bigger than the second, subtract the second from the first. If the first value is less than the second, subtract the first from the second. That's exactly what I'm saying in here. This difference is the beat frequency. In either case, either this or that, not both of them, because one of them will be negative. So the positive difference is always the beat frequency. If they are far away from each other, if F2 is 2 with the W, 2 O's, not two different, then F1, they're farly spaced between each other, then you will have two different frequencies. you will hear the waves are heard or picked up by the receiver, so you don't have to necessarily by this probe, for example, are heard separately or separated. In a sense, you will find this tone completely different from this tone, and you will hear them differently. No question about it, okay? None of them may be louder than the other, but that's another issue. But the point being in here is, and usually the intensity or the condition for the beats has to be the same. Intensities are similar. So you will hear one sound and another sound completely different. One of them high tone, one of them is low tone. Your ear will pick them up. The probe also will pick them up, okay? The problem then is when F2 and F1 are close from each other. So this is condition number one. Condition number two, if F2 is close from F1, then the two frequencies are close from each other, okay? You're hearing that sound, definitely. But there is a buildup, something in it. And that buildup is a hum. So we hear the, if you wish, the average of the two, but they're close, so either one is fine, okay? You hear the tone of one or the other. That's basically what you're gonna hear, because they're close, so it doesn't matter which one, which one is the other, okay? And a hum that corresponds to the difference of the two tones. So that is basically what's going to happen in that situation. And that is what beats are. So this is usually when we talk about beats, is this humming noise that you're going to hear it. So if you have, for example, a piano, I'm going to give you a practical example because all of this is taught probably. You have a piano and there is a specific note, for example, the C note or whatever note that the piano is supposed to be playing on a specific key. But you, as an experienced piano player, you notice that it's not producing the sound that it's supposed to do. Because the tension on it, the string that holds that note, that key, is loose or too tight, or something happened to it, okay? So the temperature, for example, will drop so that the tension in it is too much, or probably went up, the temperature, so that now the tension is less. And you have something to play, and you have to do it. So what you do in this case, you know the frequency. Let's say, for example, the frequency is supposed to be 450 hertz, because that's how it's supposed to be on that specific key. So what you do in this case, you go and get a tuning fork, just like the ones that we did in the lab, that has that frequency of 450 hertz. So you know the tuning fork is 450 hertz. You're not sure, though, if that key is 450 hertz. It could be 453 hertz. It could be 445 hertz. So it's off either too much or too little, but not 450, because you're not producing sound. So what you do in this case, you hit the note, I mean the tuning fork, and you hit the note in the same time. And since your ear is experienced, you're going to hear that note. You're going to hear the 450. There is no question about it. But you're going to hear a hum that corresponds to that difference. So if it's 453 in the string, I mean in the piano, and the tuning fork is doing 450, there is no question about it, then in this case, you're going to hear a frequency of 3 hertz. And 3 hertz is a very, very, very low frequency compared to 450. So it's going to have that sound to it. That's why we call it a hum. Okay? It's like somebody, you know, like has his mouth full of stuff. You know what I'm saying? That is basically what the low frequency would sound versus a child crying, for example, which is a high frequency. Okay? So that is the difference between them. So you will hear that hum, and it's going to repeat. It's going to repeat. So what you do in this case, you adjust the frequency. You put it, the tension, I'm sorry, you go to the tension and you tighten it a little more. One of two things could happen in that situation. Either the hum becomes even worse, in a sense, becomes even higher tone. And that means you're in good direction. Okay, that means actually you are in the right direction. Or starts to basically, you start to distinguish these two sounds. There is one clear tone of 450 coming from the tuning fork and a new tone now that is coming from the piano. So in that situation, you over-tensioned it. You need to loosen it actually. And in the first case, since now the tone is worse because that hum is becoming at a higher tone now, I mean at a lower tone, I should say, it's becoming more kind of annoying thing. That means actually you need to continue in that direction, tuning it, until at some point you hear only one sound. One tone coming from, when you hit both of them at the same time, only one tone, nothing else. No humming and no two different distinct tones. So in this case, you have tuned your instrument. The piano has been tuned. And there are people who do that for a living. Piano tuning is actually a job, and same thing actually for all musical instruments. Nowadays, they're electronically adjusted, so most of the things are not mechanical. They do them with all kinds of basically just punching the numbers and the whole thing comes in. But I'm just describing the mechanical way of doing these things. Does this thing make sense to you guys? I know probably some of you are not in the musical background, but yes. I'm not, so I know I'm not. Does this spur your interest if you have not did this, have thought about this one in the past? Maybe? Okay, well, I need you to think about it then. Maybe you guys are going to be at least interested in the future of problems like this one. As a matter of fact, it's not just in musical applications, it has applications everywhere, including, for example, in the case of resonance, when you go for an MRI, for example, a medical exam, or all kinds of applications in engineering and then also in science in general, also when you do measurements. So it's important stuff to be aware of and know how to, what's going on, at least the physics of it. It's the easiest way to explain it is actually through musical instruments in this case. So this corresponds to the beats. There is another interesting phenomenon. And by the way, this is not only true for sound, it's true for all kinds of waves too. But for sound, it's easy to understand. The other phenomenon that we need to explore in here is the concept of the Doppler effect. And I know probably we mentioned it before a little. I know actually it was in the previous oh, this is the International System of Measurements. So this is the forced oscillations. We talked about them last time. No, I don't think we get into the Doppler effect at all, because I have so many classes now. Sometimes no, we didn't get into the Doppler. Good, because I thought we did cover some of it, but no big deal. We can continue on the, we can cover it. So here is the situation. And this is a phenomenon that I'm sure also you have experienced. If not, it's easy to experience outside. If you are sitting in a bus station, for example, or even if you are sitting in your car or sitting outside, actually walking your dog or doing whatever you want to do, and there is an emergency vehicle passing by, either an ambulance or police or anything like that, or a fire, for example. Sorry about this disruption. I don't know what happened. Anyway, so we were talking about the concept of the Doppler effect. So let me finish that. So again, this is a phenomenon that you should have experienced, and it has to do with basically how the sound will sound, and it's true also for all of the waves. So here is the situation. So what we have a source, like the ambulance, for example, or police officer, or a fire truck or train or whatever source you can think of for sound. It works for any kind of source. It works also for light too, okay? It works for all kinds of waves. So you have a source in here, and the source is producing waves on its own. So if the source is stationary, if the ambulance is sitting still, it's going to produce waves. And these waves, they will travel in all directions. So this is just part of a sphere, actually. Not even a circle, a sphere that propagates in all directions, okay? So it's just looking at this side in here. So this is what I call a wavefront. So the source emits a wavefront and then waits. How long does it wait? Usually it takes a whole period, because remember, there is a period of oscillations. That is the time it takes for a wave to come next. So this one is another wavefront that was sent earlier than this, because this one just is coming off. This one was sent earlier. This one was sent earlier than the second one. So these are wave fronts, basically the front of the wave, because the wave and then another one, another one, another one. This one, in my example, is the first wave front. So this is number 1, this is number 2, this is number 3, this is number 4, this is number 5. Now, the source will wait a whole period of time, t, to emit the next wavefront. By then, this wavefront would have moved in here, and this would have moved in here, and everything shifts in that direction. Obviously, this is happening so fast, okay? Because sound travels with a speed of 343 meters per second. So if you're sitting, for example, 10 meters away, this will come in no time at all. 10 meters is far, so let alone if you are 3 meters away. So it's going to reach you very quickly, okay? So this is what happened in here. So you have the source, and you also have a receiver, in this case, a person, okay? So in here you have an observer. We call them an observer. Observer. So this is the observer. So the observer will pick up the frequency exactly of how the source does it, provided the source is not moving and the observer also is not moving. Both of them are sitting still. Then in this case, there is no problem. You will hear the tone of that frequency. If the fire truck is sitting still, for example, and sounding its alarm or whatever, the siren, and you're sitting watching it, for example, 20 meters away, you're going to hear the frequency of the fire truck. However, if the fire truck now is moving, okay, and you are still sitting still, so this one is not moving, but this one is moving. So the source is moving. So here is the situation. When it sent the first front, it's moved and sent the second one. So the separation between the first and the front, the second will be shrunk. By how much? This is where it's supposed to be. So this is the first front. This is where the second front was supposed to be, if the source is not moving. But the source moved and then emitted the second wavefront. So this is actually where the second front is. And the same thing, when it emitted the third wavefront, which was supposed to be here, it moved actually twice. It moved the first time to emit the second one, and it moved again. So it moved so that this actually, here it is where it's supposed to be. Had it moved only once, but it actually moved so that now it's supposed to be here, and so on and so forth. So the spacing between the different wavefronts is shrunk. So the wavelength actually is less and less. And remember the velocity of sound, you know how fast sound travels. It's always 343 meters per second in normal conditions. So the velocity doesn't change, but the apparent frequency now, the wavelength now is less because the spacing between the consecutive wavefronts is less and less. So the frequency now must go up to maintain the product to be the same. So you will hear a higher pitch, higher tone. That's why you can tell. That's why sounding higher and higher. Now, if the source is moving away from you, here is the situation. So the source is actually moving in this direction, and you are still sitting in here. So the wavefront now has reached you. The second wavefront was supposed to be here. But the source has moved in the opposite direction and sent it. So actually it's going to appear here. And the same thing with the third tone is going to be appearing here, and so on and so forth. The third wavefront, I should say. So the spacing actually is longer with that than what it should be. So in this situation, since lambda is higher, the frequency is lower. So in this situation, the tone, it's a lower tone. So you could tell if the source is coming to you or moving away from you. This picture still holds true if the source is actually not moving, but you are the one who's moving toward the source. So the first wavefront is in here, the second wavefront is supposed to be here, but you're going to travel to meet it. So you met the first wavefront, the second wavefront is supposed to be here, but you're going to travel to meet it. So you're going to actually take off. So the apparent actually spacing between them is also will be in some sort of a shrinking, and the tone will be higher in this case. So higher tone. Now, if you're moving away, like for example, there is a fire in here and people are trying to take it down and the source is not moving still, and you are here, you just heard the first tone and the second tone is trying to reach you, but you move away. Then in this case, it's going to take, although you're not going to be moving faster than sound, otherwise it will never reach you. But in this case, you have to be supersonic in that situation. But if you're running with normal, basically how people run, then the wave will ultimately reach you, but the tone also will be a lower tone. So in other words, if the source and the observer approach one another, a combination of both, if you wish, then the frequency is going to be higher. If they're receding from each other, combination of one moving slower than the other, whatever it is, then the frequency is going to be lower. So this is what the Doppler effect is in a sense. This is actually what the police officer does to catch people who are speeding on freeway. They use a specific frequency to send the sound, or in this case, and then depending on the return, I think they use sound, probably they use light too, okay? Depending on the frequency that comes back, there is a shift because of your motion. Now he's not moving. So in that situation, here is the situation. The source, in this case of the waves, is not moving. But you're either moving toward the cup or moving away from the cup. In either case, he's going to find how much there is a shift in frequency. You're coming to him or away from him. You're going to find, the device will tell him how much shift, how much difference in frequency you're going to have. And based on that, he's going to find your velocity. And then once he does find your velocity, he's going to issue his citation based on that, okay? Because you could be moving below the speed limit. In that situation, the device will tell him, okay, that person is fine. But if you're moving faster than the speed limit, then the shift will be higher. That's how police officers work. So the other situation also that is extensively used, and I know I have an extensive video on it I think about like 5-minute video on the lecture that you're supposed to be watching. The point being in here also it's used extensively in astronomy also for light. As galaxies are moving away from us, their frequencies. So if you take spectrum, which is part of the next lab, by the way. So if you take, for example, hydrogen has specific lines on its spectrum, okay? And from the red all the way to the blue, okay? Those are the characteristics of hydrogen. So what happened in this situation, you try to measure this spectrum of light for that galaxy, and you will find that the red is actually redder, is here, not here. And this one is actually here, and this line is here, and all of the lines have shifted toward the red. They're not necessarily red, but they are moved in this direction. So we say in this case is this galaxy is moving, and how fast is moving depending on this red shift. That's, by the way, how James Webb is working right now. It's measuring this red shift, how much there is a shift toward the red for faraway galaxies. Some galaxies are actually moving towards us. So this whole thing will shift towards the blue. So those are blue shifted. Some stars, for example, part of a binary system. So you have a star moving in, going in circles around the other star, and we're here looking at it. So this is from our vantage point looking at these stars. When this star is moving in this direction, it's going to be red shifted. When it's coming in this direction, it's going to be blue shifted. When it's in here, it's not shifted at all. In other words, this spectrum will stay in this place. So the spectrum will dance, will go back and forth. Okay. Based on that dance, you're going to determine the period, and you're going to determine all kinds of properties in here. So this stuff is important. It has a lot of implications in science. It has applications in real life. I mean, and all kinds of things in here. So it's important things. What time are we still here? Okay, we still have good time. Okay. So these are some of the ideas that are needed to be covered in this chapter 15, or yeah. And then we still have to introduce chapter 16, I should say, and we still have to introduce some of the concepts from chapter 17, but those are going to be technically tackled upon next week. Hopefully by next week, the situation with the office on campus will be fixed, and we will not have these problems that we had today, and actually on Monday too. So I'm picking up the book, and hopefully you guys still have access to the book, either online or in physical book. And I'm looking at page 349, and I'm going to post this one on Canvas so that you guys have the assignments. This is a homework assignment. Again, you're not supposed to submit it. You're not going to be graded on it, but I'm going to assume that you guys are doing it. Some of the homework I'm going to collect, I'm going to grade, but this one I'm going to assume that you guys are doing it. And if you have difficulty with it, please let me know so that we can have discuss them in person and so on and so forth. Okay. So the problems I have listed in here for you, and again, they're going to be posted on Canvas, so don't worry if you don't get them right now. They're from page 349 on the book, and they are problems 63, 65, 74, 75, and then 78, 85, and 87. Okay, they're all on the same page. Okay, they're all on the same page, so hopefully you guys will have time to go through them. And if you have difficulty, and this message goes actually for the people who are live or the people who are actually watching this recording, please do not hesitate to send me a message. There will be a session during the lab time. It's not this coming lab time, but another lab time where we'll dedicate it just to answering all of this kind of problems, so that we have, when we come exam time, you guys are 100% ready, whether for the multiple choice part of it or the problem solving part of it, because there will be a version where you're going to be asked to solve problems like this ones. So problem 63, for example, it says in here, the musical note middle C has a frequency of 262 hertz. So when I said earlier 450, it's because I don't know nothing about music, okay? So apparently the middle C is at 262 hertz, okay? So what is the period of vibrations? Okay, so let me do this one quickly here with you guys and see what relationship we're going to do. I know some of you probably took physics before, so this is kind of easy, but let me share the screen. Let me open a new page in here, which I'm going to call problems. Again, let me write them down. So what we're looking at is page 349. The problems are 63. Let me make this one bigger font because I don't like this too small fonts in here. I don't think you'll see it or not. Let me make it into like 28. Okay. 63, 65, 74, 75, 78, 85, and 87. Okay, So these are the problems I selected from this one. This is your homework assignment. And again, you're not going to submit at least this ones, but you're supposed to do them, okay? You're supposed to do them on your own time. Make sure you understand them. If you have difficulty with any one of these or the whole thing, please do not hesitate to send me a message. The last thing I would want you to do is be frustrated not knowing how to do these things, because they're supposed to reinforce what we've been talking about, to teach you about them, basically to learn what these things are, okay? So that if you have never done these things before, you'll be comfortable with it. Some of you are not majoring into the engineering later on to take the more advanced courses in physics or probably math and things like that. So you don't care about all of the math stuff, but we need to understand how these things are related. So problem 63. I'm going to pick a few of them today, and then I'm going to leave the rest for you guys. So problem 63, it says the musical note C, middle C, has a frequency of 262 hertz. When you're reading problems like this one, it's a good idea to write the main points so that you can come back to them. And that's all it's given. And it says what is the period of vibration. So it's asking basically, what is the period of oscillation T? Now, what relationship I should use? Remember, when we started this one, it was in this side. When we introduced the first one in here, we related the frequency and the period to one another. And that relationship is here. The period is the inverse of the frequency. So I'm going to use that one because all I am given is the frequency of this problem, and I'm asked to find the period. So all I am going to do then is say, okay, the period actually is just 1 over the frequency. And 1 over 262 hertz, that is what I'm supposed to do. And I'm going to carry out this one because there is something that's probably for those of you who are not taking physics, it might be what's the deal with that basically. So I minimize that window. So let me stop this one just to show you that. Do I have a calculator on this computer? Hold on, calculator. I have a very lousy calculator, so I'm going to share that with you. I'm sorry. Okay. So let me start sharing again the calculator just to show you how you would do it on a calculator. So on this calculator on the computer, this is the Windows calculator. So I'm going to take 1 and divide it by 262, exactly how it's written. There are some functions in here that I could take advantage of, but I'm going to, for right now, let's use this plain thing. So it's giving me this whole big number, 0.003816 and a bunch of other numbers, okay? Technically, I know the frequency up to 3 digits because they tell me it's 262. So all of these 3 digits are relevant. It's not 260. It's not 270. It's not 200, but I know it up to the ones. So I know the hundreds being 2, I know the tens being 6, and I know also the ones being 2. I don't know what decimal point it is. It could be 262.5, it could be 262.3, 262.2. That is not important. As a matter of fact, it could be 261.7, and it's still 262. So we call this one Sig Figs. I know we discussed it earlier in the last week, but that's basically the point here. So what am I looking at? And I'm looking at more than 3. I'm looking, first of all, these leading zeros, they are not significant figures. It starts from the first digit, and any 0 of that is actually significant. So if I were up to this point where there is a 0 after the 7 and the 9, and if I need to retain this many, that 0 is significant. But these 3 zeros are actually not significant. So what are the significant numbers there? 3 for sure, 8 for sure, 1 I need to consider. I mean, I must consider. But the question I need to ask is it really a 1 or is it a 2? How would I determine that? And then I ask myself the next number after that. Is it 5 or more? If it is 5 or more, I have to round up. I have to say that this number is actually a 2, not a 1. If it is less than 5, then the answer would be a 1. So in this situation, I ask, is the 6 5 or more? And the answer, yes. It doesn't matter. If it's a 5, if it's 6, if it's a 7, it doesn't matter. 9, it doesn't matter. As long as I answer the answer to this question, is it a 5 or more? Then I need to promote the 1 to 2, and I'm done. Then the significant figures in this case are 3, 8, and 2, not 1. Okay, so that's how you read it. Calculators like this one, they are dummy. They don't understand these things. They don't know what we're doing. But we know what we're doing. We know that the frequency is known up to 3 numbers. So the period that I'm going to find from this frequency must be known only up to 3 numbers. So if somebody comes in here and say, you know what, the answer is 0.0038167938993, whatever digits he decides to stop on or continue all the way through, that person is not honest in science. That person is not true to science because he's making false claims. What are these false claims? He's claiming to know the period up to that precision. He claims to know, or she claims to know, the period up to that many digits of precision. And that is not true, because the only measurement he or she did is based on 3 significant figures only. So in order to be honest, we have to answer that question with that much certitude, with much certainty in it. So since we know the frequency up to 3 digits, the only acceptable answer is the one with 3 digits, up to 3 digits. Because here is the problem. I could have made another measurement that I needed for my experience, for my experiment, for example, and that measurement, for example, gave me a value for, I don't know, with 2 significant figures only. Then that basically negates the 3 precision that I have from the frequency. Then everything has to be done up to basically the 2 significant figures. So it is important to remember that when it comes to experiments, when it comes to number representations, usually you are as good as or as strong as your weakest precision. It's like your weakest thing, if you wish. So that's what the answer is. So it's 0.00382. That's really what this whole thing is. So let me go back and share that screen and now represent the answer. So it's 0.00382. And now the other issue that I wanted to illustrate with this one here. What units for time? It's seconds, because 1/Hertz is actually a second, or 1/second is actually a Hertz. This is in honor of Mr. Hertz, that's all, because he worked on this thing. So we gave the unit of 1/second, we gave it a name in his honor, okay? But the second is actually the unit for period. Obviously, this is not in scientific representation. So what I do in this case is I have to move the decimal point 1, 2, and 3. Again, why would I do that? I want to bring the number to make it in a scientific representation so that it's a 10 to a power of something, okay? Since this number is less than 10, then in this case, I have to multiply it by 10 to bring it. This number, I ask, is this number, because this is what the whole scientific representation is, this number must be greater than 1, greater or equal to 1, and less than 9, less than or equal to 10, or less than or equal to 9, less than 10, basically. That's the whole point of it. That's what 9 is, okay? It has to be less than 10. So here is the question. I ask, is this number 0.00382 greater than or equal to 1? The answer is no. So in order to make it greater than or equal to 10, I have to multiply it by 10 first to see what's happened. So if I have 0.00382 and multiply it by 10, all I have to do is just move the decimal point, and the answer will be, because the 0 doesn't make any sense now to retain. So I'm going to write it for a moment. So this is then the result of the that product. So this 0 now doesn't mean anything. So it's just the leading 0 only before the decimal point. So in this case, this is the answer if I multiply it by a single 10. I ask another question. Is this number greater than or equal to 1? And the answer is not. It's less than that. So the answer is no. As long as I continue, the answer is no. I have to multiply it by another 10 again. So if I multiply by 10, again, the calculator will give me 0, 0. Remember, I'm not writing this 0 anymore because I disregarded it. And there is a 3A2. That is if I multiply, I'm going to disregard this one and then ask the same question. Is this number greater than or equal to 1? And the answer is no, because 0.382 is less than 1. So what I should do in this case, multiply it by another 10. And the answer is going to be 3.82. That is the answer to it. There is a leading 0, but I'm going to drop it anyway because 0.3 is 3. So the question is this number greater than or equal to 10? And the answer to that question now is, is yes. It is greater than or equal to 1. As a matter of fact, 3.82 is more than 1. I need to ask another question before I move forward. Is this number less than 10? If it is, and it is, because 3.82 is less than 10, then I have found my answer in here. So it's 3.82. Then I need to know, what is this power? Since I multiplied by 10, and multiplied by 10, and multiplied by 10 3 times, I have to actually divide by 10, that same 10 3 times. So I have to divide by 1,000, and 1,000 divided by 10 is 10 to the negative 3. That's basically what this thing in here. So this is negative 3. So the answer really, in scientific representation, you could leave it in here in a homework assignment and you're good. You don't have to worry about it. Or you could write it as 3.82 times 10 to the negative 3 seconds. I'm not going to be picky about these things. Please do not write more digits in here that you really should. And I'm going to comment on it in the first time around so that you guys know that this is too much. You don't need that many. But don't tell me it's 0.0382 either, because that's too little. 0.38, for example, if somebody decides, you know what, the answer is 3.8 times 10 to the negative 3. That is actually too little. Too little. Not, I don't mean an answer. I mean, it's not. It's giving me an ambiguity on here, but I know that's actually 2. I know the answer is this much. But this is more precise. So this is my point in here that hopefully you guys are trying to understand. Now, forget about everything else. Here is the relationship. That is the main thing that you're supposed to do. And you're supposed to do this fraction and get the answer in here. And if you have difficulty with these things, please let me know. I know sometimes I tend to be too verbose, but I'm trying to get you guys to move through the next level, okay, at the same time too. Okay. This stuff is not easy, I know, even for some calc-based students. So if you're having difficulty with it, please don't feel kind of so it's not really and it's not big deal at this point. As I was saying, if you give me a different representation of this one, I'm going to accept it. You're going to get credit for it, but you're going to get a comment from me. That's all. Okay. And the scientific notation also is not required. So you could leave the answer in here. And again, I would rather see it in finalized form if I can. If not, then don't worry about it. But the units is a big deal. I'm going to really make a big fuss over that. So you really have to make sure that the units are correct, okay? So that is how we're going to be doing these things, okay? Now, the other problem I thought we should discuss is 74. Any questions? You have the chat in here?
No.
Very good, thank you. So 74, it says your sonic range finder measures the distance to a nearby building at 20 meters. So you have a sonic device, so you have a building in here, and you have a device in here that sends waves, sound waves, and based on when they come back, and decides the distance is 20 meters. Okay. The range finder is calibrated for sound traveling at 343 meters per second. This is tricky. This is very tricky, okay? In other words, this device was calibrated at 300 when the velocity of sound is 343 meters per second. That is basically what this device is. However, you didn't tell it that the temperature is different. The temperature is actually negative 37 degrees. It was a super cold day. Negative 37 for degrees. I mean, it's like negative what, 40 Fahrenheit, super cold, okay? Well below freezing. You're somewhere in Alaska, and even on that day, it's an extremely cold day on that day, okay? And now the velocity of sound actually, if you did, it should have been 309 meters per second, because sound travels, the speed of sound depends actually on the temperature also. So the question is, how far is actually the building? Because your device is telling you it's 20 meters, so the distance is not really 20 meters. So here is the question. Let's say, for example, the distance is some unknown distance, okay? And the sound went out and came back, and it took a time, okay? A certain time, okay? At 343 meters per second, it gave you a distance of 20 meters, okay? So that is the time it took for it to go back and forth to measure this distance. Obviously, you can find the time in here, which is just to divide the distance by the speed, and you're going to find the time it takes for the wave to go out and come back. But the distance has to be multiplied by 2, because the sound is going, coming back. So the distance then in this case is 40 meters to give you this time. Or if you wish, you're going to have half the time. Either case, you're going to find the time in this situation. But the actual speed is less than that. It's actually 309 meters per second. So you take that time that you measured for the time to go back and forth. And since the distance is actually less, because here is the deal. This one sent a wave and received it after a while, and you measured the time it took for it to go back and forth, okay? But the distance is actually not 20 meters. That's actually further away, I'm sorry. It's this much, okay? So the time it took to go back and forth, that time when this first phase was sent and received, covered the longer, should I say longer distance? No, it's going to be a small. Okay, let's follow the algebra. Forget about it again. So we're going to use the algebra to decide in here, because we're toward the end and my brain is started to basically. Anyway, so you find the time. So from here, you're going to find the time, okay? So it's going to be 40 meters, because 2 times 20 is 40 divided by 343. And you plug it into this expression, and the distance should be less, yes. Okay. So went back and came forth at slower speed, okay, because the temperature was super cold. That's why it's going to be less distance. So now you're going to find the distance traveled, which is going to be basically using that time, which is 220 divided by 344. But now time is the actual distance, which is 309 meters. But this is the overall distance back and forth, okay? So whatever it is, you're going to divide it by half. So at the end of the day, the answer is going to be 309 over 343 divided times 20, okay? So we can do the algebra in here and find what the actual distance is. Do I still have my calculator in here for some reason? This one is. Okay. Let me do the numbers in here. So I have 309 times 20 divided by 343. So the answer is only 18 meters. Okay, so that's the correct answer. 18.01 meters. Again, if I do the calculation in here and put, let me share with you the share the calculation again, so that we have the same level of. So this is what the calculator is giving me. I know the speeds up to 3 sig figs. Okay. But for some reason, when we measured the time, we retained only 2 sig figs, or at the end of the day, the distance was measured, was found to be with 2 sig figs. So I'm assuming that these numbers are all with the correct sig figs. So in here, to retain 2 sig figs, that means anything after the 8, which is a decimal point in here, and the 0, I ask myself, is this number greater than the 0, that is this greater than or equal to 5? And the answer is no. So in this case, you just leave it as is. I don't have to promote it upward. Done. It's 18. Or if I consider the answer is actually with 3 sig figs and the 20 was a precise number, or it was actually rounded also to being 20 exactly, then in this situation, I ask myself, the 18 is for sure. 0.0 is for sure. I mean, 0 could be 1. That's a question. I ask the number that comes after that, the 1, is it more than or equal to 5? And the answer is no. So in this situation, it's 18.0. And in either case, the answer is 18 meters. So that is my point in here also. So what this thing is giving me then is that, so I multiplied by 1/2 already, is the distance is 18 meters. Okay, that is the distance that I should have found. It's just slightly less because the sound is actually moving slower than what it should have been for the same amount of time. Okay, that it went. So the building is actually closer to me in here than the first time when I thought the sound is moving super fast at 343 meters per second. So this is 74. Okay. The last one I was thinking to consider today with you guys is 78, which is really following the resonance that we talked about in here. 78. I'll put it in the book in here closer for me. 78 says the following. You measure all of the possible resonant frequencies for a guitar string in the range from 500 to 1,000 hertz. You have a device, you can measure frequencies between 500 and 1,000 hertz and find that it will resonate only, so there is resonance at 600 hertz, at 750 hertz, and at 900 hertz, that is. Okay, so the question is, what is the fundamental frequency for the string? Again, I'm supposed to find the least common multiple, the greatest common denominator, not the least common multiple of this number. So which number I can divide by all of these numbers at the same time? And the answer is going to be 150 also. Here is why. Because 600 can be divided by 10. This one can be divided by 10, and this one can be divided by 10. Don't put 100, because if you put 100, yes, 600 divided by 100 is 6. 900 divided by 100 is 9. But this 750 divided by 100 is 7.5, and that is not good. So you need a number where the answer is going to be a full integer number, not a decimal point. So 10 works for all three of them. This will give me 60. This will give me 75. This will give me 100. As a matter of fact, if I do the divisions in all of these three numbers, I find 16 here, I find 75 in here, and I find 19 here. These numbers, they can be divided by 3 easily, okay? They can be divided by 3 easily. The reason why is because 6 is a multiple of 3. 7 and 5, they add up to 12, and that's a multiple of 3, so I know it can be divided. And 9 is a multiple by 3. 0 doesn't count in this case. So this one divided by 3, which is also a common multiple of all of these numbers. 60 divided by 3 is 20. 75 divided by 3 is 15. No, it's 25, I'm sorry. 90 divided by 3 is 30. Now, these numbers happen to have also another multiple together, and that multiple is actually a 5, because 20 divided by 5, any number that ends up with a 0 or a 5 can be divided by 5 still. So since this one ends with 0, it can be divided by 5. Since this number ends by 5, it can be divided by 5. Since this number ends with a 0, it can be divided by 5. 20 divided by 5 is 4. 25 divided by 5 is 5. And 30 divided by 5 is actually 6. Now, there is no greater denominator in here for these three numbers. 4 can be divided by 1, which will give me 4. 1 never counts in this case, always true. So we have to ask 2 and 4, that's it. This one can be divided by 1, which we are not going to consider, but 5 only. As a matter of fact, 5 is a prime number. Since we reach a prime number and it's not in any of these two numbers, so we reach the bottom line. In other words, this one can be divided by 2 and this one can be divided by 2. This will give me 2 if I divide it by 2, and this one will give me 3 if I divide it by 2, but this cannot be divided by 2. This can be divided by 3 to give me 2. This cannot be divided by 3. This cannot be divided by 3. So at the end, we're stuck. So what I say in this case is I have 5, which is a common multiple. I have 3, which is a common multiple. And I have also a common divisor, not a multiple, I should say. Sorry about that. So the product of these three numbers is the greatest common denominator. Yes, 5 is common denominator. 3 is a common denominator. 10 is a common denominator. 2 is also a common denominator because it's part of the 10. So all of these numbers are good, but their product will give me the greatest common denominator. So it is 10 times 3 times 5. That is 150 also. So this is something that you should have learned in algebra. But if you have difficulty with it, please do not hesitate to let me know and I should be able to help you. If not, you can plug it in calculators, and some calculators online, they give you the answer. And that's fine, as long as you can find the answer. So this question is then the fundamental frequency is 150 hertz. That is the greatest common denominator of all of these measured values. Sorry about that. Again, I think I need to really so anyway, so we found the fundamental frequency. I don't know if we were able to record it or not, but let me go back into my notes and we're going to end it right now. So hopefully we can finish. I was going to finish on these problems and introduce the next chapter. So basically, this is the fundamental frequency that we found, which is 150. So the 600 is 4 times the fundamental frequency, and that's why I put the index in here on the first measurement. The second measurement, which happened to be 750, that is 500 times 150. Okay, so that's the 5th harmonic, and the 900 hertz is actually 6 times 150. I mean, you can divide and you will see that it's true. So this is 6 times 150. And that is equal to 900 hertz. So those are the measured values between 500 and 1,000. So the point being in here is you find the greatest common denominator of all of the measured values. That should be your fundamental frequency. And that's the answer to the question, actually. That's it. We don't really need to do this. This is not part of the question, just to help you guys understand the topic at hand. And that's the whole purpose of this exam, this exercises, these problems that you're supposed to be doing. Anyway, the rest of them are supposed to be part of a homework assignment. So I'm going to post that on Canvas. And you're not supposed to submit this one. Hopefully you guys will learn from it. Okay, the next units, the next chapter is chapter 17, which we're supposed to start next week anyway, on Monday. And that is chapter on light. So we're going to introduce the concept of light. We're going to have a model for light. We're going to explore the concept of reflection of light, the concept of refraction of light, which is easier than the case of sound. And then also we're going to explore the different things that we can do with that, namely the instruments that we can make with that. Mirrors, for example, that reflect light, lenses that refract light. And then we have all kinds of mirrors. We have flat mirrors, we have concave mirrors, convex mirrors, and we also have same thing with also for lenses. Lenses, you can have convex, concave, and also a mixture of the two. One side is concave, otherwise convex. Some of the applications are actually in photography. For example, they use lenses a lot. In glass, for example, making in optics, they have instruments, they use that a lot. And also telescopes and all kinds of other applications. We use for magnifications and things like that. They have applications in this thing. The other thing also is, since we're introducing light, we're going to discover that it has spectrum. Light, if you run it through, for example, even through a lens, what is going to happen to it is that the white light, that is, is going to be broken. So the first time we're going to be talking about a monochromatic light with only given frequency, specific tone, if you wish, if you want to talk about it as a sound. Then it exhibits all of the things that I mentioned earlier. However, when light comes in bunched together with different frequencies, then its behavior depends on its wavelength. The blue light, which has a short wavelength, and the red light, which has a longer wavelength, and anywhere in between them is the visible spectrum that we see. This we're going to explore actually in the lab also. We're going to have a source of light for different gases, and based on that, we're going to determine the different frequencies that we have in there, okay? So this is all part of next week. And I'm going to post this assignment on Canvas, and I'm also going to post the recording, hopefully see if there is any disruption in it, and then post it. And sorry for these problems again that keep on, I think it's either this one or hopefully when we go back into the office, it's resolved, then I will not have these problems. Thank you, guys.
Bye, Professor.
Thank you, bye.